And then once we have a unit cell, so now we will work with the unit cell. Now each and every point or position in the unit cell needs to be represented. How do you represent that? So these are called crystallographic points. How do you represent a crystallographic point? Okay. So you have this unit cell A, B and C and XYZ axis. So let us say the edge length, this edge length is A, edge length is B, edge length is, this edge length is C. Okay. So now if you want to describe this point P, the way that you describe is you take the position and you sort of find out the projections of the point, right, on the coordinate axis, and what is the fraction, right. For instance, this distance is q times a, q is the fraction, and this distance is r times b, and that distance is s times c. Then you define your crystallographic point as q or s. You do not write in an absolute value, you only write in terms of your lattice vector, that is important. And when you are representing a crystallographic point, you just simply write these three numbers besides each other, that is all. You just write three numbers. For instance, if you, let me see if I have an example, yes. So this is your point 1 by 4, 1, 1 by 2. So what I need to do? I need to move 1/4 in this direction. So let us say this is 0.48, 0.56, 0.5. You actually do not need to do this calculation in principle. You know what is this distance, you move 1/4 of this distance and so on. So if you move, do the calculation, this is 0.12 units or nanometers, right. So you move 0.12 in the x direction, 0.56 because this is 1, right, that will be full length, and then half of it 0.25, and that will be your point, right. So you can, this is the way that we represent crystallographic point. It is pretty elementary, but it is important that we know how to represent. Whenever you are reading a textbook or a research article, if somebody is talking about crystallography and they represent something like this, you should identify that they are actually talking about a crystallographic point, nothing else. Okay. So depending upon this lattice parameters, the actual values may differ, but this position is actually related to the fraction along the lattice direction, vector direction. All right. So now if you have a body centered cubic structure, this is how a body centered cubic structure looks like, and I have only shown points at the appropriate locations, right. And now how do you represent the lattice points there, right. So 1 is at 0, 0, 0. So you write the coordinates. This is how you represent all the lattice points, right. 1, 2, 3, 4, and the fifth one is the body center. So half, 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 and so on. Is this clear? Yeah. For FCC, can you do that? For FCC, pretty straightforward, right. What will be the point on one of the faces? One of the faces. 1 half, half. Why 2 halves? Okay, you write it down. I will not think about it, you think about it. Okay. Next one, very important thing, the ability to identify crystallographic directions is one of the most important activity in this course, because this is going to tell us a lot about the mechanical properties. Okay. So we should be able to identify crystallographic directions properly, and if somebody gives you a crystallographic direction, you should be able to understand what direction they are talking about. Okay. So how do you represent the crystallographic directions? The crystallographic direction is basically a vector, a line between 2 points or a vector, right? So now how do you represent this direction? Using some indices. So how do we determine the directional indices? So first what we do is, the vector is positioned to pass through the origin. So you may have vector anywhere, but then you can actually translate it such that it goes through the origin. That is the first thing that you will do. Or you move the unit cell such that one of the ends of the vector meets the origin. Both of them are possible. Both of them are equal. And the length of the vector projected on each axis is measured in terms of unit cell dimensions, right? Like what we have done for point. It is very similar to point. And then the three numbers that you get are multiplied by a common factor. This is the difference between writing a point coordinates and the directional indices. Once you know the fractions, what you do is, you multiply that with a common factor to reduce to a smallest integer. We will see what it means. And then let us say those numbers that you got are u, v and w, and then you enclose them in a square bracket. That is how you represent a crystallographic direction. So now, when somebody tells you that 100, you should immediately understand that it is the representation of a crystallographic direction. They will not tell you. The fact that it is enclosed between square brackets tells you that it is a crystallographic direction. That is something that you should be aware of. Okay. And now you need to draw these three crystallographic directions, right? The projection onto x-axis is 1 and y and z-axis are zeros. So what should be that one? The unit vector, the vector along x-axis, and the length of the vector is equal to coordinate, sorry, unit cell lattice parameter in the term, right? Similarly, 110, that guy, and 111 will be that guy, right? So can you tell me how do you write the directional indices for this guy? So normally what will you do? First you have to write the projections onto each coordinate axis. What is the projection onto x-axis? Half. What is the projection onto y-axis? What is the projection onto z? Very good. Then what you need to do? You need to multiply these numbers with a common factor, so that you will bring it to a smallest possible integer except 0, smallest possible number. So that will means you multiply it with 2, then this becomes 1, 2, 0, right? And then what will you do? You should not stop there. Unless you put the bracket, you are not telling the world that it is actually a crystallographic direction. That is very important, right? So a by 2, the projection is actually, you should not write 1 by 2. So it is actually a by 2, b 0. Then you will only write the fractions, projections onto the fraction. So 1/2, 1, 0, and multiply it with 2, 1, 2, 0, and then that will be your. Okay. So like that you should be able to write crystallographic directions for anything, right? Now, what is this direction? 1, 1 bar 0. So you are only talking about, always we said positive directions, but you can also have negative direction, right? So you don't write -1 when you are talking about crystallographic directions. The -1 is represented as 1 bar. Okay. So let us say this is your unit cell, and now you need to draw this particular direction. So how will you do? This is your XYZ. What will you do? You can actually move this guy this way, right? So this guy can be considered, you can actually draw something like that, right? and then that will be your new axis. Sorry, this is your new axis, not that one. And then one is this y, and -1 will be in this direction. So that should be your right. So that will be your 1 bar base. So now you will be able to draw any crystallographic direction, identify any crystallographic direction. Alright. So another important concept and extremely useful concept. For crystal structures, what do you mean by an equivalent crystallographic direction? You can have several non-parallel directions. They need not be parallel. That is the key here. You can have several non-parallel directions with different indices, but they can be equivalent. What is the meaning of that? That means the spacing of atoms along each direction should be the same. So 1 0 0 in the previous one, what is 1 0 0? In a cube, in a cubic crystal, A equal to B equal to C, isn't it? In a cubic crystal, A equal to B equal to C. So if I draw this direction, that is 1 0 0, and this direction 0 0 1, and this direction 1 0 0 1 0, right? All these three directions. Now if I am here, by moving a distance of A, I am finding my next point. Similarly, here as well, by moving the same amount of distance, I am finding my next point. Here also, I am able to find the next point, right? That means the distance between points in all these crystallographic directions are the same. And if that is so, then they are called equivalent directions. Okay? They are not parallel, but they are similar. They are equivalent, right? Because this is only true for, it need not be true for other unit cells. For cubic unit cell, it will definitely hold good. So for cubic crystals, 1 0 0, 1 bar 0 0, 0 1 0, 0 1 bar 0, 0 0 1, 0 0 1 bar, all of them are equivalent. So this set of directions are called equivalent directions, and then we can, because all of them are equivalent, we can group them into a family, and that is what we call equivalent, a family of equivalent crystallographic directions. And if you want to represent a family, the family of these crystallographic directions are represented by these brackets. And when you write 1 0 0, this actually means all permutations and combinations of 1 0 0. So 1 0 0 can be 1 0 0. You need to have only 2 zeros and 1 1s. That's all it means. So it need not be 1 0 0, 0 1 0, 0 0 1. Again 1 bar 0 0, 1 and 1 bar again, and then you have all the combinations. That is why this is called a family of 1 0 0 directions. All these directions are equivalent. And to represent a family of crystallographic directions, the enclosure is a different enclosure. That is the enclosure. Okay. So by that argument, if you have a crystallographic direction 1 2 3 in a cubic crystal, that must be equivalent to 2 bar 1 3 bar, or 2 bar 1 bar 3 bar, or 2 1 3 bar, any combination of 1 2 3. All of them are equivalent. Okay. So if you know one direction, so you don't have to worry about other combinations. All of them will behave the same. This is important because then we will see when we are talking about mechanical properties, certain properties of the material or certain deformation mechanisms in the materials are governed by how atoms are arranged on the crystallographic direction. Okay. And please note that this condition that we have just now discussed of representation of equivalent directions need not be true for other crystals. For instance, it is not true for tetragonal, because tetragonal, when you are moving in 1 0 0 direction and 0 1 0 direction, you will have to move by a different amount, absolute amount, to actually reach to the lattice point. Is that clear? So, all right. So, I think we will stop here.